Welcome back. Today's day is going to be kind of dedicated to monsoon predictions. We have 3 1-hour talks in the sense of pedagogical sense, followed by lunch, and then usual hands-on session in the afternoon. And in the evening, we will have a plenary talk. So our first speaker is Dr. Suryachandra Rao. He's a senior scientist and associate mission director for Monsoon mission at IITM Pune. Thank you, Dr. Rao, for coming all the way.
Okay, good morning, all of you. And first of all, thanks to the organizers for inviting me to give this lecture on the forecasts of monsoons. So as the title suggests, I will be talking about forecast skills in present monsoon mission models and what is the roadmap for future. So this is not my work alone. There are about 50 scientists who have worked for this monsoon mission, and you'll see that there are so many people who have contributed to making this mission successful. So this is the outline of my presentation. First, I will try to impress upon what are the challenges in predicting monsoon, particularly at seasonal timescales. So that is actually true for any other timescale as well. So then, what are the strategies we have followed in trying to improve the skills in the models? And so still, there is a lot of way to go forward further for improving it further. So what is the roadmap for future improvements that also we'll talk about. And so Monsoon mission is a national mission mode project of Ministry of Earth Sciences. So it started in 2012. So it has completed 2 phases already. So in the first phase, what we did is that we just borrowed a model from NCEP. NCEP is National Center for Environmental Predictions in USA. So then we try to look at how well the monsoon is simulated and what are the skills of the models. Like that, we try to look at the models. So before that, we have done an exercise of understanding what are the present models at that time, 2012. What is the skill of the models? So this is very famous paper by Gilles and Srinivasan, which was published just before monsoon mission started. So what they have done is that they have taken standalone atmospheric model and given the observed SSTs, force the atmospheric model with observed SSTs. So, and this is the period from 1985 to 2004, they have carried out the handcasts. And if you look at the skill of that models, the maximum skill you can achieve is about 0.20. So actually this cannot be called as a forecast skill because the observed SSTs are used to make the forecast. So basically it should be considered as a potential predictability limit. So that is if you are using only atmospheric model. So if it is 0.2 means we know that not useful forecast can be made. So then there have been, IMD has a long history of making seasonal forecast using empirical models. It's almost 150 years old organization, and they have been using empirical models to make the forecast. And if you look at for same period, the skill of the models is about minus 0.12. That means as good as not having it. So then the coupled models. So coupled models were started being used very efficiently at leading centers that time. So though coupled models are having a very good skill in predicting ENSO, but when it comes to monsoon, the skill is only 0.09. So this is the benchmark when we started the monsoon mission. So we know that these are the skills we have to improve upon and try to understand how do we do that. So this is a paper by Wang et al. So he has shown very clearly if he is taking a period of 1989 to 2012, the correlation is using observed the coupled models is minus 0.12, that is what is shown there. And if you use clip models is 0.24, and statistical model and all, this is for another period, it is 0.09. So this is the way they are said very clearly that. And the reason Bin Wang et al. They gave a reason is that because there are two modes of ENSO in the tropical first week, and present day models are unable to get those two modes correctly. So that's why monsoon prediction is very, very low. So with this background, we started working on monsoon mission and started trying to find what are the problems and how do we resolve them. So this is the model borrowed from NCEP, and also COLA also helped us in getting this model. So we started, the atmospheric model of the borrowed model is actually about 100-kilometer resolution, but we have changed it to 38 kilometer. That is one thing we have done. And there's a novel land surface model, SIS, CIS model, a coupler. A coupler is hard-coded, means each and every grid of the atmospheric model is hard-coded to the ocean model or land model. So it was very difficult to make any changes to this model. So that is another challenge. And ocean model, when we started working is the MOM version 4.0, and it was about 0.5 degrees everywhere and 0.25 in the tropics and 40 levels. So this was the system that was made operational at IMD also after making some improvements in at least increase the resolution. So what additions we have done in this model framework is that we started generating our own initial conditions at, for example, atmospheric initial conditions. We started taking it from NCMRWF and ocean initial conditions from INCOIS, Hyderabad. And the runoff is very crudely prescribed. That is one value for throughout. So this is the model that we started using it. And actually, once we have increased the resolution itself, we started getting very good results itself. So whatever we have seen 0.2 in the atmospheric model has jumped to, or 0.09 couple model has jumped to 0.47 or 0.4, about 0.5 almost in this model. So if you look at the problems with these models, that though I am mentioning that these are the problems for CFS model, but these problems are there for any model, any couple model you take across the globe. So these problems are there everywhere. So what is that? The cool SST bias in tropics, except in Eastern Pacific, you see that there are two blobs of warm SST bias in the tropical Pacific, and dry bias over inner landmass. You can see that T126, we used to have very strong, almost 80% bias. If it is 8 millimeters per day is the seasonal average, we used to get about 2 millimeters or 3 millimeters per day. So that was the, so this almost, there is no monsoon over Indian region. So when we increase the resolution to 38 kilometers or 35 kilometers, then the bias started decreasing a little bit. And SSTs also started warming here and there, but there is no clear pattern. So then also the diurnal amplitude. We all know that the diurnal cycle rectifies into intraseasonal scale, and intraseasonal rectifies onto seasonal. So if you look at the diurnal amplitudes, the phases, they are not very well captured in these models. Again, this is not only for this model. You take any coupled model across the globe, situation is same. So though they are having different flavors of the same thing, but every model suffers with the same biases. So there is no single exception to that. Some may be having very serious biases, some may be having less biases. That's all the story. So the another one is ISO to total variance is overestimated. So ISO is so much of very strong in the couple models. So by looking at all these things, then we thought if we have to make a strong impact, so we have to address these biases at least and try to see how we can address these biases. So as we said, we started working on different schemes. So Partha is here. He is the one who has introduced us to new SAS scheme in the MMCFS model. So you all maybe by now fully familiar with what is the Arkawa-Schubert scheme and Arkawa-Schubert to how it has become SAS. Then afterwards, new SAS is Han and Pan have developed this scheme, and these are the different modifications have been done. Convective trigger, cloud top selection, momentum transfer, cloud bakes, mass flux, all these things have been modified so that you get where you need to get the convection, that right place at where there is updrafts, that is where you should get that. So also increase the convection strength. All that happened because of new SAS. Then we only realized like that we have done several experiments actually. So there are more than 60, 70 model sensitivity experiments have been carried out to understand and reduce this bias. So I'll just give you some of those examples. So you can see that A2O is there, but beyond there are so many, but I'm not showing all of them. So this is the control run where we have done the hindcast is 2003 to 2017, and the resolution is, so one thing that we have always done is that whenever you do the development work, carry out first in the low resolution model, T126. So if it is successful, then use it at high resolution. So this is the philosophy we have followed throughout. But some of you can ask, what is the guarantee that whatever worked at low resolution will work at high resolution? But we all know that the computational resources are not infinite. You have to work with what is given to you so that when you are doing so many experiments at very high resolution, data management will become a big issue, and also the computational resources will become another issue. So that is the why we have started following this strategy, that first try to implement everything in low resolution model, then see it how the high resolution model is getting benefited afterwards if we are really. So when you see that these are the skills of all India summer monsoon rainfall with GPCP as the reference point. So what all we have achieved, the skills have improved, is brackets we are given what is the increment in the skill when you have implemented a particular scheme. So this is the control run that is done. So it was 0.33, and the improvement after correcting some of the bugs, we have borrowed models so that we started getting about plus 9% improvement in this one. So again, the NCEP model, whatever, using the NCEP initial conditions, here we are using our own initial conditions. If you use NCEP initial conditions, this is the model. But you have to notice that the hindcast period varies from one run to other run. So whenever we are making comparisons, we are taking exact same hindcast period to make the comparisons or the improvements. Okay. So there is a COLA also has identified several bugs in the model, and they have given us, and when we do that, skill is not so promising, 0.29 only. So then these are the 4 experiments which are done on convective parameter scheme by doing several SAS2 and adding shallow convections, all those things. What you see very clearly is that when you actually work with convective scheme, the skill jumps by almost 91%, means almost doubles. So that is one good thing about this one. Then we realized that we are getting these improvements for wrong results. So you have to get the things correctly for right reasons. So what happened when you try to do this, because the clouds are increasing as expected in new SAS, and the convection is increasing, the amount of solar radiation that is reaching surface is decreasing significantly. Therefore, the cold SST bias that we have seen before is becoming worse. So actually it is raining over cold SST regions. So that itself tells you very clearly that we are getting something wrong. But the results are very encouraging. So then we realize that it is one most important improvement that we have to do is in the convective scheme. And that has to be there, and try to find out what are the other ways of alternate ways of improving these other biases that are cropping up because of this. So our new version of the model has this new SAS scheme, but your SSTs are now reasonable. So we have done all that changes. So there is another run we have done, the albedos prescribed from the satellite observations, where the non-ice albedos were prescribed. And this is the only development that has resulted in reducing the skill. Almost 60% skill has dropped now. So maybe it is the fine tuning because of these albedo effects has now taken fully into that account, but all other models have shown clear improvements from the control run. So the other one is if you have used only inchoate initial conditions, then also you get 42% improvement in the. So what is that? The NCEP initial conditions and our own initial conditions shown a lot of improvement compared to what NCEP uses. So because the techniques of creating the data simulation also different in our this one, though we have borrowed from them, but we have improved upon those simulation techniques. So this is the high resolution. High resolution also 0.51 is the scale, that is about 76% improvement. So one thing that you notice from all this slide is that there is a lot of developments have happened, and almost all development activities that we have taken up are showing improvement in the scale. So Nino 3 also, you see that some good improvements. Once we have added SAS, you get 0.7. But the problem is that, as I told you in the beginning itself, this is a hard-coded coupler. So if I have to incorporate all of these things into the borrowed model from NCEP, then it is almost impossible. So what is that we have to do? Then first thing we have to remove that hard-coded coupler and bring in a very friendly coupler where you can add several components. So that is what we have done. And again, fortunately, the new version of the model shows much better skill than any of these developments. So in spite of all these efforts, there are some intrinsic challenges that are there for predicting monsoon. So that should be very clear to all of us. So how do we make this forecast, and what are the intrinsic challenges that are there? So this is a slide from Professor Shukla, who gave a lecture in item Madden-Julian lecture in our institute. So he has shown very nicely that the anomaly correlation coefficient of the coupled models from the same model is reaches about 0.8 in recent periods, whereas it is 0.7 in the earlier periods. You can easily attribute this to the observational network that is there, Tau observational network that is there in the tropical Pacific, that has really made a difference to the skill of the models because the initial conditions are better. Whereas if you look at, this is Nino 3.4 scale and this is monsoon rainfall scale in the same model that we borrowed. So you see the difference between SST prediction that happens in the tropical Pacific is 0.7, whereas when it comes to monsoon rainfall prediction, it is only 0.2. So that actually exactly matches with the first slide that I showed you. So this is the big gap that is there. So that is the reason the world community is so much afraid to touch about monsoon. The simulations are difficult, improving skills are difficult. So once upon a time, WCRP, World Climate Research Program, identified monsoon prediction is one of the grand challenging problems. But within 2-3 years, they have removed that grand challenge. The reason is simple, because no breakthrough is happening. So that is the reason why we have started monsoon mission. So this is our problem, and we have to address that problem. So if you look at again JJS, this is for shorter period, it is 0.29. This for longer period, 62 years, it is 0.29. In 62 years, the ENSO monsoon relation was very strong in these years. So even the statistical models used to work very better. The skill used to be 0.9. because only ENSO is to determine your monsoon. So, as I mentioned in the previous slide, ENSO is the major modulator of interannual variability of monsoon. That we all know that, correct? So, but the biggest challenge is that in spite of knowing that ENSO is the strongest modulator, we have to make forecasts of ENSO in the spring. So this is the variability explained by different initial conditions. If I use February initial conditions, the variability that I can capture in the coupled models is about 5 to 10%. March may reach about 30%, April is also about 30. So, but if you come to summer months, the variability explained by these initial conditions is more than 60 to 80% or sometimes 90%. So making a forecast in the summer months, trying to predict December, January, February SSTs is much more lucrative, means the forecasts are much more reliable. So what we call this less variability explained with these initial conditions is the spring predictability barrier. If you initialize your models in the spring, then ENSO skill will not be very good. So in spite of strong association with ENSO, but this is the problem, that is intrinsic problem. This spring predictability barrier will be there, though some people show that in some of the models it is gone, but it will come back very soon once they change the hindcast period. So this is the biggest challenge. So how do we address this challenge? Until unless you try to improve the prediction skills of this season. If you use initial conditions from the spring and try to improve the skill of the ENSO, you cannot make appropriate monsoon predictions. So this is the challenge one. So this is what all of you students, particularly the scientists, have to look at. How do we address this problem? Okay, this is the challenge number one. So if you look at, if for example, these are the CS5 20th century simulations are done. So if you look at whenever we start forecasting the spring, the skills are much, much lower. Whereas if you start with summer, the skills are much better, reaches almost 0.8, 0.9. So only in recent periods, they started improving, but not as good as before. So the challenge number two is that what is shown here is that the standard deviation and standard deviation mean ratio. Standard deviation is shaded and ratio is are the lines. So if you look at only 20% of variability is seen or less than 20% of the variability is seen over the monsoon. Whereas if you look at tropical first week, the variability is much more than 60%. So the signal itself is very strong elsewhere. Whereas over monsoon region, the signal that we are trying to capture is very, very weak. So if you look at the all India summer monsoon rainfall and the deviations are plus or minus 10%. So the standard deviation is only 10% of the mean. Okay, so here you are showing 20%, but mostly over the oceans. But the same ocean in the same latitude belt, you see that when it comes to first week, it can explain 60% of the variability is 60%. So predicting something like this is much more easy than where the signal itself is very, very weak. Okay, so it is a blown up map, and you can see that over Indian region, it is not much variability. So the challenge number three. So you cannot change that at all. The challenge number two, you cannot increase the amplitude or the variability so we have to work with that only. So the challenges, they will be there throughout. No matter what development you do, these are the challenges will remain. So we have to find ways to address that. So this is another biggest challenge. Though ENSO monsoon relation is very strong, but these models, different models are there here. They actually, this is only MMCFS is shown, but it is, again, you remember that whatever I show you here, the problems are same for across the models. So they show very clearly JJS that, these are the observations. The correlation is very, very weak actually in the recent periods. But if you look at the models, they are doubled or sometimes triple. So there is a strong ENSO monsoon association in the coupled models. So how do we address that? This can be addressed, but not the first two challenges. Okay. So then we notice that is basically because when the synaptic variability, that is low pressure systems, are very, very strong in the months of July and August, that coupled models are unable to get them properly. So the synaptic variability is completely missing in the month of August. That is the reason what we notice that unless you improve the synaptic variability in the models, the ENSO monsoon relation will not improve in the models. So the other challenge number 4 is this is coming from that only, the earlier slide, where the synaptic variability is contributing to ENSO monsoon overestimation of the relation. And if you look at these different, this is GPCP, MMCFS, CCSM, 4 and floor B, GFDL floor B models. So this is the total variance and June, July, August, September, and JJS together. So this is the ratio of synaptic scale 2 to 10 days band pass filtered variance to total variance. So this is the monsoon band. You can see that everything is underestimated in the couple models. Somehow floor B, GFDL floor B gets some of the variability. So, but in that model also the ENSO monsoon relation is again overestimated because it is actually underestimated in spite of doing better than other models, still underestimation is there. So basically what we have learned from all these challenges is that the most important thing to improve the monsoon forecast is that look at small scale. Not only spatially, in the temporal also. Until unless you try to improve the dynacycle, you cannot get seasonal mean much better. And similarly, if you don't resolve the eddies, particularly in the oceans, particularly in the Bay of Bengal. Bay of Bengal, we all know that it is highly stratified basin because the fresh water that is coming from the rivers to Bay of Bengal. So therefore, it creates much more eddies compared to any other basin. So how do we get those eddies? So these are the lessons we have learned, and we are able to address challenge number 4 and 3. But 1 and 2 will remain forever. So this is the new version of the model. We can call it almost Indian version, but I should say very clearly that individual components are developed by somebody else. So for example, MOM version 6 model is developed by GFDL and GFSL was developed by NSAP. But here again, Parda here, that group has done changing the dynamical core TCO. So that once we couple this to this, then it becomes much more indigenous model. So then you can ask, why are we using still models that are being developed elsewhere and bringing it? So we don't want to again reinvent the wheel. E is equal to mc square, is equal to mc square, whether you do it or whether it's done outside. Okay. So we have to take it from where some foundation is already there. So that is the principle we have followed in the monsoon mission. We don't want to rewrite the whole equations and momentum equations and try to solve them. Okay, so we have biogeochemistry, and good thing is that now we have also aerosols in this model. And so one good thing is that we have a river routing model and also core 3 flux algorithm, and we are trying to add ocean wave model as well. So these are the different things that have been added, and you can easily call it as an indigenous model because a lot of developments have happened. And in fact, after we have done this work, the other centers like GFDL, NCAR, they started implementing these things. So actually river routing model was there in the long simulations, that is climate projections runs. But then nobody has ever used it at seasonal scale. So that is what we have done in this model, and we have shown that particularly Bay of Bengal stratification is very important. Until unless you get that stratification correctly and the eddies in the Bay of Bengal correctly, you cannot improve your monsoon simulations. So the people started asking us, how did you do this? And what is the code changes you have made? So how you have taken the budgets and all that. So we have provided guidance on incorporating this in other models now. Okay, again, core 3 was there for a very long time. Fourth is a flux algorithm. So we all know that most of the models use bulk flux or NCAR flux algorithm. So we started using core 3 flux algorithm. And that has actually made a lot of difference for resolving the diurnal scale, diurnal amplitude. So therefore, the ISO variance, total variance ratio also started becoming close to observations. And the synaptic variability also improved. So, and most importantly, there is a development happened in the Monsoon mission is that earlier, even now also, most of the centers do the individual component analysis from the atmospheric model and ocean model. So we have started working on weakly coupled, and it is now established that it does better. So, and that we are working now towards strongly coupled data simulation, wherein ocean will dictate that state of atmosphere will dictate the state of oceans. So that is being worked out. And once that is also incorporated, the skills started improving better, particularly at weakly coupled timescales. Okay. So these are the papers which are already published. We can have a look at it to get the more details. So this is the Monsoon mission model, the first version of the model. And these are the different models across USA and also in the Europe. So this is the Monsoon mission model. You can see that it stands out clearly from the other models. So you can see that almost all models are clustered together. The scale is still about 0.2, 0.3 only. This is the Taylor plot. And the variance is very much underestimated. Means the model is trying to get every time the normal monsoon. Like empirical model, it also gets normal monsoon. So the internal variability is not well captured by none of these coupled models. So for any model development, while developing, you can always call it as a very good skills. But the real acid test goes when you are actually making operational forecast. So as I told you, we have started Monsoon mission in 2012, but the experiment started from 2011 onwards. So these are the statistical model skills. This is the dynamical model. And these are the, so because this model was handed over to IMD, what they do is sometimes they use April initial conditions, sometimes March initial conditions, so mix up for various reasons. So operational, you cannot say that you have to use only this because of several constraints they face every time that they need forecasts, maybe sometimes very early. Cabinet will call for forecasts, so yeah, they have to give them. So the skills of these models, you can see that very clearly. First stage means the forecasts which are issued sometime in April. So these are actually real forecast. Here, the second stage means already monsoon started. June, July, August, September, or August, September, they give that. So the skill is not really the skill of the monsoon. So the skill of the statistical model is about 0.33. Whereas if you look at dynamical models, with whatever setup IMD has, still it is better than statistical models. But if they have done what we have told them, use April initial conditions only. And if they do everything actually that, the skill using the old version of the model is close to 0.6 and the new version is close to 0.75. So this itself will tell you very clearly, this is the acid test for any model and real-time performance. So even this, the number of years are not very high, but this is what it tells you very clearly, that 0.74. So you just imagine the first slide, 0.2 is the potential predictability using the AGCMs. Our coupled models 0.09. From there to 0.74, that is what is Monsoon mission achieved. And this is the new model now. The number one is MMCFS version 2 new model. Again, it shows the supremacy compared to other models. Because what we try to do in this is that whatever biases we have identified, whatever experiments we have done, we try to incorporate most of them. And now you see that why this success, you can easily ask me why this happened so easily. It didn't happen so easily. We have done 50 to 60 experiments to understand what is required to be done. So the new SAS scheme, which was giving wrong results, for wrong reasons, it's giving right results. So now that also we have corrected. Now your SST is not cool anymore. In fact, it is slightly warmer compared to the, so warmer SST is expected to give more rainfall. So that relation is very well preserved in the new version of the model. So this is the skill that I showed you, that MMCFS1, GPCP and IMD. This is the internal variability of ISMR. The skill is, as I said, 0.722, 0.74. And most importantly, so here it is not next. So the RMSE, if you make any forecast, what is important is that your RMSE, root mean square error, should be better than the standard deviation or less than that. So if your model has some errors which are much more than the signal itself, then it doesn't make appropriate forecast. That is true even for NINO 3.4. Unless you normalize it, it is not going to give you correct results there. So, but one good thing that we have achieved is that the normalized root mean square error is less than 1 in the new version of the model. So that means the forecasts are becoming much more reliable. Okay. And this is the teleconnections with ASMR. Again, MMCFS, the old version, has 0.83, and MMCFS2, slight improvement, 0.75, but still it is overestimation only. Still we have to work on this. Observation is showing only 0.64. So still there is overestimation, but not as bad as other models. So this is one of the reasons why the skill is improving. Not only that, if you look at the skill of AMM at Atlantic Meridional Mode, then also it is coming very close to observations, 0.18 to 0.15 in the. So things have improved a lot, not only the SST metrics, but also the precipitation metrics. So the teleconnections started becoming better, not as good as observations, but better than what we started with. So that's why we started getting good results. So now, so when you say something like this, there are enough skeptics saying that you have selected a particular period, particular years, so that you want to show your model is doing better. So this is all reviewers. Myself will also ask the same question. So they also ask me the same question. So this is the first, when we published this paper, we have done it from 1980 to 2020. So we have shown the skill of 0.74. So then naturally the reviewer started asking, what is the guarantee that if you move to other period, this superiority that what you are showing still remains. So what we try to convince the reviewer is that we have plotted running sliding correlation for 11 years. And what you see clearly is that if you look at these models, so here I am showing you other next generation models from GFDL and also UK Met Office. Even ECMWF also I have it, but that was already published, so I'm not showing. But again, you see that MMCFS2 gives you 0.72 or CIS5, that is UK Met Office 0.55. So still we are maintaining that. And for longer period, CIS5 is not there. So if you look at there also, you see that our skills are much better than GFDL sphere model. Okay. So even if you look at the sliding correlations, again, the superiority of MMCFS version 2, the red line, that is very clearly on top at any given window you take. And most importantly, there is the ISMR teleconnections undergoes different phases. So this is the observations. So it was very, very weak during the period of from 90s to 2000s, early 2000s. So the teleconnection is very, very weak. But none of the model gets that. Except MMCFS version 2 has some variations. They are not as good as observations. So if you look at GFDL sphere, it is almost constant, a line which is vary from this period to this period, that is the blue line, goes all the way without any variations. So that epochal changes that happens that are not at all captured in GFDL sphere. But MMCFS version 2 gets some variations which are not as good as observations. At least getting that is a good sign. So getting here is another challenge that again we'll keep working. So there is a lot of work still open for many researchers to work on this problem. So that is about seasonal, and we have forecasts that have been done at extended range timescales also. And this is the same model, that MMCFS version model was used for this, but what they do is they take different ensembles from different physics components, Arkawa-Schubert, revised Arkawa-Schubert, Ferrier macrophysics, Java and Carr. So like that, they create a multi-model ensembles using different physics, okay? And they are run at T574, then changed to T382. So that also has shown very strong improvement, particularly in the week 3, the forecast, particularly over the monsoon zone, where the most of the rainfall happens. You see that there is 88% increase in the scale compared to the previous version of the model. So all these things are happening because we started looking at monsoon very focusedly. So how to improve the monsoon simulations and how to improve the biases. Improve the biases means reduce the biases in the models. So that is the only success mantra here. So we are fully focused towards monsoon and try to see that how do we improve, keep improving that. But one thing that after this monsoon mission, whenever I make this presentation outside of India, so everybody appreciates that monsoon being the strongest convection center during summer. If you don't get correctly in your models, you are not going to get good results elsewhere else. So now, whatever grand challenging problem they have been thought for some time, then left it in between, they started now thinking that this is the only way we can improve the skills of other regions. Because it is very simple. You have the strongest convection center in the summer season sitting over Head Bay of Bengal. If you don't have that in your model, how do you get the tailcashes correct? Correct? So improving monsoon simulations is in the interest of the whole world community, not just for Indians. This is the message they got it very clearly. And then now people started incorporating most of the things that we have done. Even Partha has done that stochastic parameterization, not stochastic, multi-cloud, multi-physics, stochastic plan scheme that also they are trying to incorporate in NCAR model. So whatever developments we have initiated, everybody else is now started working on those problems because that is the interest of everybody now. So if monsoon mission is successful, that is one of the success stories. We are able to convince the global partners that this is the thing that you still have to get it in your models. So again, not only the whole monsoon core region, if you look at the subdivisions also, particularly week 3, you see that the skills are improved, particularly the central Indian region. So improvements are seen in every small domains like subdivisions also. So I think Partha will cover most of this, correct? Extremes and short and medium range forecasts. So I just want to tell you that the monsoon mission, when we started, this is one of the first results we got, that whatever day 3 forecasts, the accuracy of the day 3 forecasts used to be there before monsoon mission, we could achieve day 5 forecast with the same scale. That means we have gained 2 days lead time in making the same forecast with same reliability in the short and medium range forecast as well. So not only that, you can look at, there are different papers. As you increase the resolution, the skills have improved everywhere. And these are different ETS, PSS, HS skills. You see this everywhere, the message is same. That monsoon mission is able to actually gain lead time of 2 days in improving the forecast. Anywhere else in the world, it takes for 1 day to gain 1 day, it takes more than a decade. So within 1 decade, so we are lucky. We don't say that something great has happened. Here we have increased the resolutions, then we could get it. So it has happened within 5 years after starting the monsoon mission. Huh? Yeah. So now the challenge is to move it beyond 5 days. That is the real challenge. And he may be covering the extreme events, getting extreme events. Morning only send me a paper that nothing is good in the model for extremes. So that is another challenge that I have to add to my number of challenges. Okay, but that is workable by using other techniques as. So they also, we have started ensemble prediction system at very high resolution. At the time of we implemented, no other center in the globe are using at that resolution, that many members for ensemble forecasting system. Again, you see that these are the RMSE track errors. RMSE of track position. So as you can see that the ensemble, if you use, instead of using a single ensemble, you use the ensemble mean, the RMS is less in use ensemble forecasting system. So things have started working, and also extremes, though he says that here Kerala event he could capture by saying that the number of standard deviations is, but the model itself don't have the extremes, so its standard deviation itself is low. So he has come up with a mechanism where, okay, if it is extreme for the model, so can we use that information? So that way he showed that yes, we could get some information for extremes also. But if you look at only physics part of it or quantum of rainfall, that still we are far away from the reality. Okay, we don't get that much of quantum of rainfall for extremes. Okay, so this is another important slide. Once the TCO was implemented at IITM, so at the same time GFS FE3 version, that is NCEP, they also started. So both the models have changed the dynamical core at the same time. So normally we have a tendency to believe that GFDL does better than us. That is for sure because they have a lot of experience. The number of people work on those problems are huge. So therefore, it is a good hypothesis think that they can do better than our models. But then we have made a comparison of TCO with FE3. You don't see much difference between these two. If at all, day 3 and day 5, slight improvements are there. But I don't call it as real improvements. So with the limited human resources, limited computational resources, implementing the TCO has really made as good as some other leading centers. Okay. So this is the model development strategy that we have been followed for so far. So we have increased the resolutions. So that has really resulted in a lot of improvements because it is expected once you increase the resolutions, the small scale features are well resolved. So therefore, as I mentioned in the first slides, getting small scale is more important for getting the large scale correct. So that has really helped. And also dynamical core also we started semi-Lagrangian TCO. So that is all this have made a lot of changes to that. And also the MOM4 0.5 to 0.25 changed to 0.25 to 0.25. So resolution is giving some results. But blindly increasing resolution is not the answer at all. So unless you improve these parts, initial conditions and physics. So there are so many other ways to do it, but what we are trying to do is, we are trying to do these components at this moment. Then we will go to ocean model mixing schemes. Now there is a AML based mixing schemes that are coming. So that also we are trying to implement. 4.3 itself, estimating the CD from different observations is very challenging. So what we have did, we have created a AML algorithm. Now we have implemented to decide some of these coefficients. So that is also is giving good results. But Right now, I'm not going to show it because it is work yet to be published. So we also have done microphysics in different models, convective parameters, and all these things we have been doing it. Now the roadmap is keep improving these things and try to get this also. This is the new paradigm shift that we all have to think about it. So how to bring in AML models, make use of them best, so that most of the things that can be addressed by these things also. So in fact, I will show you next slide. Okay, these are the different AML models. You have forecast net, graphcast. This is the graphcast skills for different regions, homogeneous regions over India. This is all India. So graphcast is doing definitely better. You take any time, day 1, day 3 forecast, day 5 forecast, or even day 7 forecast. Graphcast does much better job than our traditional models. So when it comes to forecast net, if you use, this is the forecast net model. If you use only Indian data, the skills are not as good. So that itself tells us very clearly that even though it is short range forecast, but the reality is that you need to have the large scale or the global scale phenomenon into the model. So once you use global, then the skills are better. So these are the lessons we have learned from these AML approaches. So there is no way we can get rid of AML models because they are showing very good results, at least short and medium range. So STS timescales, seasonal timescales, they're yet to evolve much better way. So whatever skills achieved by AML models are as good as the traditional dynamical models for S2S and seasonal, maybe decadal also. Okay. So these are the AML. We have to take it very seriously, and each and every component of the models, each and every step of the model, like creating initial conditions, post-processing, everything can be done by using AML. So that is the way forward for improving the skills further. Particularly, one thing that I want to tell you is that if you are trying to increase the resolutions, now we are talking about exascale models at 1 kilometer resolution. So developing or something, so at 1 kilometer also parameter schemes will be there for some reason, for some components, okay? So, but getting observations at that scale is almost impossible. So then still we have to use AML. Then you can ask me a question, if you don't have the enough data, then how can you create AML models? Then you have to go to physics informed neural networks. So there are ways of doing it, but actually in India, we are yet to take advantage of this in a very big scale. Okay, so this is the things that can will change a lot of things that way, the way we do it. Even the TCO model or our MMCFS version 2 model takes more time to run the model compared to the old version. But you know that operationally, if you have to make a forecast, you have to give the forecast before the event happens with long leads. So that again can achieve through AMLs. So to understand where the model is getting problems and how to make the faster. So this is the roadmap that we have to, all of us to think. So recently we have started one Prithvi AA program in ministry under as a part of Mission Monsoon. So, but this is nothing to do with the ML models that are being incorporated in the models. This is the dissemination of the information. So what we came up with is that, like ChatGPT, we have named it as Monsoon GPT. So create the models, first use the large language models, then move to large multi-models, so that impact assessments also can be done, or impact-based forecasts also can be done by using multi-models. So I'm not going to give you more details because it is an NDA between the industry and us. So we are not supposed to give more details, but something like ChatGPT, Monsoon GPT is going to come, and it will be reality very soon. At least we are targeting for next 2 years, at least a prototype of Monsoon GPT be ready. So this is the message from the presentation. Dynamical models are really improving. It is not that they are stuck. There's a lot of improvements, a lot of scope for improvement. And we have shown in examples how to improve them. Definitely, convective prevention is one of the bottlenecks. The whole agenda of this workshop is that, and getting that correctly for right reasons, if you're getting good results, that is the most important message. So if you have to accelerate the growth, so now 0.74 is reached. So reaching from 0.74 to 0.75 or 0.76 is going to be very difficult. So that can achieve only through AML, by marrying AML to the dynamical models. And the Monsoon GPT, we are targeting in next 2 years to get a prototype. So actually this has come directly from Prime Minister's office, that we are always, as a weather forecasters or climate forecasters, what we do is we just display our information over website or through some app. But the real information, that is actually we are pushing the information. So what the Prime Minister actually gave a direction to the Ministry of Earth Sciences is that you have to pull the information. Like, for example, a farmer is there. He don't know where to look for. So you just have to ask you guys or the app or anything that, can I do this practice of sowing the seeds tomorrow? So you should get an answer. So that is the pulling of the information by the farmer. So we have to get ready. So that's why this is the challenge given from by top. So we are working on that. So if you want more details, here itself you see that there are 50 others. So this is the publishing BAMS. The second phase of the monsoon also is now being prepared for BAMS again. So you'll get almost all the results that I have presented on this two different. There's a Clever Exchanges dedicated issue for monsoon mission. There also you can look at it. So this is one good thing that happened. There is a ICTS, is a agricultural center, international center. What they do is they take the forecast from us, both extended range, short range, seasonal, and brief the farmers. If there is a delay of 2-3 days, the farmers will keep asking them, when are you coming to tell us? Because they have to. So that reliability of the forecasts have improved. That's why you see, this is only one place. Like that, they do it for 4 or 5 districts. So the reliability has, particularly at least the people's mindset has changed that, okay, at least if you use this forecast, we will be benefited. Okay, with that, I thank you again, the organizers, for inviting me. If any questions are there, I'll take. Thank you.
Thank you, Dr. Rao. I think we have a few minutes for questions.
Yeah, you can speak loudly. Okay.
Thank you, sir, for highlighting all the problems, all 4 challenges. And I saw from the presentation that you relied on high resolution and some teleconnections to resolve the challenges. So my question is, do we have correlation matrix for example, sometime high resolution is capturing local phenomenon and giving a better forecast, but sometimes teleconnections are necessary for that. So do we have a correlation, weighted correlation matrix between them for a prediction?
So we have not done the way you are asking, but in our papers we have explained very clearly that once you improve the small scale features, so there is one paper, what is that LPS paper? Where is it submitted? IJOC. So that paper shows you that resolving the small scale eddies in the Bay of Bengal or the dinocycle. Dinocycle is already published. You can see that paper by Pradhan et al. So improving that actually improves. So we have not tried to segregate this so far, but that is a very good idea, and we'll try to look at how to address that problem. So whether the increasing resolution has made the change or the teleconnections. It's a good
You
idea.
can also learn by AIML model as you are saying.
Yes.
And the other question, sir, can we go back to that slide, the new forecast system? Yeah, this one. Here, I want to understand the bias part, where the biases are in all the model, whether atmospheric model, land model, biases are everywhere assessed and corrected, or we are correcting the bias only after forecast. I'm not.
Okay. So the biases are there if you are looking at an individual component. See, for example, I am telling you that there is a strong dry bias over Indian landmass. So that is in coupled models. So we try to understand whether it is coming from the ocean model or atmospheric model. So in fact, atmospheric standalone model gives you over estimation of the rainfall, at least first few days. So afterwards only error will grow. So then we realize that it is mostly, say once you look at seasonal scale, the ocean plays a very important role because memory is there. So we try to improve the diurnal cycle in the ocean model, SSTs and all that. So it is a very tough job, very involved job to understand from where it is coming and what we have to do. So each and every experiment has been done by following that criteria.
Sir, if one has to do bias correction by data-driven way, so is there any way we can access this atmospheric model, land model of?
I will be very happy to give you that.
Thank you, sir.
So there is a ARDC website, ardc.propmed.res.in, correct? Or you just Google it, ARDC IATM. You will get that data center. And if you ask for a particular data center, we will upload that also.
Okay. Last question. Bias needs truth and forecast, right? Observation and forecast to correct the bias. So what are the reliable data sources for that? Specifically, I'm asking about a forecast because observation data sets are there. So forecasting data where we can get.
That is where the ARDC will get that forecast data.
Okay, okay.
So all our short and medium is being uploaded every day.
Okay.
Seasonal, once in a month. So for some reason, you think that the variables that are given there are not sufficient. You want more data. You can always write to, there is a email address there that I want this data to be uploaded. So within 1 month, they will upload the data.
Thank you. Thank you so much.
Okay.
Yes, thanks.
Yeah, thank you, Dr. Rao. That was a very nice talk and very encouraging to see the progress that's being made. I was wondering about the hybrid strategy that you mentioned with the AI and the dynamical one. And so nowadays, when people say hybrid, it could mean multiple things. It could be just having data-driven models in an ensemble, or it could be nudging the dynamical model with a different data-driven model. It could be AI components within a model. And could you elaborate on the strategy when you mentioned this hybrid?
So the basic thing that I'm trying to tell here is that hybrid means you have to use both the dynamical models, the forecast made by the dynamical models, and the AML models, and also incorporate these AML in the parameter schemes. So that is what is the hybrid nature of this AML. If you try to train your model only based on observations, for example, you try to predict extreme rainfall events. That never happened in the data period. Okay, so you don't have that information in that data. So that information you could get better way from the forecast. What Partha has developed, that if the model itself it thinks that it is an extreme event, though it is not exactly extreme as per the observations. So that information has to be used, then only you can make a progress in. If you use only data-driven observation models, I don't think you can make.
So in this case, it would be having an ensemble of both dynamical and data-driven models.
Yes.
Yeah, which we guess that the prediction of extremes would be better by dynamic?
No. If you don't use the information, train the models using the dynamical models, then I don't think you can get better information. Not just create the ensembles with AML models, which are driven only by the observations.
Yeah.
Try to do that hybrid approach. As far as my understanding goes, it will not work.
There's time for one more question. I was wondering about, so in the first half where you showed the comparison of the MMCFS and GFDL with the ENSO, and you showed that the correlation of the GFDL model was just
Flat.
yeah, I mean, there's no variability there. So there is variability in the MMCFS, but it seemed out of phase with the correlation
I agree.
of observations.
So first step is to get the variability. Okay, so then try to get the phase also correctly. So this is what we have achieved. The next step is to get the phase also correctly.
Okay, yeah, thank you.
See, all problems cannot be addressed in one single go.
Thank you, sir. My question is same parameterization scheme used for different resolutions, or is it necessary to modify the parameterization schemes
There are actually
based on resolution?
different. So MMCFS version 2, we have a scale-aware parameter schemes, both in the oceans and the atmosphere. So you have to change. But when you go to the 1 kilometer resolution, that is what I was telling, that AML has to come to your rescue.
The next question is scale of the forecast is defined as correlation between observed and predicted anomalies. So why is it so, and why is it not defined directly based on the difference between observed and predicted values?
RMS is also there, no? I shown that.
Thank you.
Any other questions?
See, there are so many metrics to estimate the skills. But easy way to communicate is through correlation coefficients. So that way you can easily connect. So there are ROC curves and all that, but you try to complicate the things.
Any other quick questions? Maybe, okay. Just keep it quick.
Physics informed?
Neural networks. You have mentioned physics informed neural networks can be the future for forecasting. So how is
that is what we believe, because nobody has ever tested so far. So that is the move forward, the way forward to improve that. Because as I said to his question, you don't have extremes in the observational records. So if you get some information from your dynamical models that my instability is going like this, or moisture convergence is happening like this, then can I get a extreme event of this magnitude? So that has to be through physics informed.
Thanks.
Yeah, let's thank Dr. Rao again for a very nice